All right, differential equations is like a big topic. There are several further courses that can be taught on it, partly because things can get complicated quickly, but mostly because it's just such an applicable idea. Any mathematical modeling is going to have its roots in differential equations. And when I say mathematical modeling, I mean taking some sort of real world situation and trying to figure out how it works. So that can be anything from modeling like animal populations, so their growth rates maybe with some sort of predator-prey system, crops up a ton in physics when doing any kind of kinematics or thermodynamics or electronics. And it crops up a lot in the news these days when trying to get a model for how some sort of virus growth rate is going to work. All of these ideas have their roots in differential equations. Differential equations is what's driving these systems. If you can reflect some underlying assumption in an equation, in what we're going to describe as a differential equation, then we can figure out what possible model can fit that assumption. Okay, so certainly a big idea, but in these last couple weeks, we're going to be doing sort of the introduction, getting our feet wet, having some sort of idea of what this idea of a differential equation entails. So with a differential equation, we're trying to find some function that meets a condition. And I want to contrast this with a typical, if I had said an equation before now, sort of, we're going to call this an algebraic equation. I want to contrast this differential equation idea to something that we've seen before. Specifically, if we have the equation, let's say x squared minus x plus 6 equals 0, then what we mean by this equation is, or what we mean by solving this equation, is that we want to find the value of x that when plugged in makes this equation true. And we could do this a couple ways. We could factor it, we could do quadratic formula. Either way, you should get that, well, when x equals 3, if I were to plug in 3, that's going to make this equation true. So that we say that that's a solution to the equation. You might notice that you could also plug in -2. So because this is a quadratic, there ends up being 2 solutions to this equation, this particular equation. Okay, when solving an algebraic equation, we're looking for a numerical answer. I want to contrast this to a differential equation, which is going to, differential equation, something like 6 times the derivative of our function, 6 times our function plus the derivative of our function equals the second derivative of our function. Okay, and there's a bunch of different ways of writing an equation like this. So because there's a bunch of different ways of talking about a function, we might sometimes call our function y, like if we're plotting a line, y equals mx plus b, we're talking about the function y. Depending on the context, we also often write our function as f of x. So this same equation, just written in a different format, would be 6 times our function f of x plus the derivative of f of x equals the second derivative of f of x. Right. And just for completion's sake, we can also write this equation using what's called the Leibniz derivative notation, which you you're maybe more familiar with it being the dy over dx derivative format. So 6y plus dy dx equals d squared y dy squared. Oops, I'm sorry. D squared y dy squared. Okay, anyway, so all 3 of these things are different ways of writing down the same idea. So with our algebraic equation, we wanted some number that made these equations work. Now we're looking for some function that if I take that function and maybe also take a couple derivatives and plug those things into our equation, then that holds. So we're going to be talking a lot about how we can come up with these functions, but I wanted to point out that I'm going to call this f1 of x being e to the negative 2x works for this equation. And we can check that. One option, if you want, you can pause the video and calculate these things and plug it in. So I'll give you a second if you want to do that. Okay, we can also just go through it together. If our function is e to the negative 2x, then we could also find the derivative of this function. Thankfully, this is an easy function to differentiate. We just get negative 2 e to the negative 2x. And we also need our second derivative because it shows up over here. We're going to see that this is 4e to the negative 2x. Now, if I were to arrange these, if I were to plug these into the equation in question, so it would be any one of these, but I'm going to use this middle one because I already started using f notations. 6 times e to the negative 2x, so 6 times our function, plus negative 2 e to the negative 2x should equal our, so that was our first derivative, should equal our second derivative, 4 e to the negative 2x. And we can see that, yes, this does in fact hold. Therefore, this f1 of x is a solution to the differential equation. That's our goal. So for the rest of the semester, we're talking about differential equations. We're going to be finding functions that solve this. So I did want to point out that with an algebraic equation, we typically have one or two, or maybe sometimes several solutions to the equation. With this differential equation, we're actually going to just about always have infinitely many. Like if we have one, we're going to have a whole class of them. And a big part that we're going to be talking about is how to keep track of sort of how many parameters can we change? How many degrees of freedom do we have for solving this? So I want to go and point out that we can do the same thing with another function. If f2 of x is e to the 3x, this is a completely different function, but when plugged into this expression should also work. And as it turns out, if we put any constant in front of these, oh, that's not quite true. There are ways of putting in constants to make this also work. So there are going to be infinitely many solutions to this differential equation. Here are 2 of them.